Okay, so we have done the following. So we are discussing trace class operators and Hilbert-Schmidt operators. So we define trace class operators as all those T in B of H such that trace of mod T is less than infinity. Okay, where we know mod T is T star T, which is a positive operator. So we take the square root of that. This is mod T of any operator. So that has finite trace. So that is what is called trace class operators. We also defined Hilbert-Schmidt operators, which are all those T in B of H. Trace of T star T is less than infinity. And we have shown that BTH is Hilbert space with respect to the following inner product. This is a Hilbert-Schmidt operator. This is a Hilbert-Schmidt inner product defined using the trace on B to H, which is equal to trace of S star T. So we have shown this is a Hilbert space. And further, we proved that B1H is a Banach space. So we want to see what is its dual. And we have already remarked that C0, I mean, if you have C0 sequences converging to 0 will correspond to compact operators, and L1 sequences will correspond to, this is the non-commutative analog of that. Okay, L1 sequences will correspond to, I hope you hear me. So L1 sequences will corresponds to B1H, and L2 will correspond to B2H. So we want to get similar result like this. So we want to prove the following theorem. We want to prove that the dual of trace class operators, which is like L1, is like L infinity, which is B of H. And also we want to prove the dual of all compact operators is all trace class operator with the corresponding norm, with the trace norm, and with the compact operator, the norm is just the L infinity norm. I mean, it's a uniform norm. And B of H is also a uniform norm. And here we have the trace norm. We use the trace norm, which is like L1 norm. This is like non-commutative LP spaces. We can similarly define LP spaces using the trace. Okay, and the same duality will hold through there. But we are only discussing L1. We are only discussing the trace class operator. So we want to prove the following. So, okay, let me write the theorem. So for any T in B1H, maybe I will define it before and then go to that theorem. Okay, definition. For any T in B1H, which is trace class operators, define phi T from, this is what K0 is, right? We use the notation K, not B0. Usually the notation is B0 for that, but I used K, so let me continue with that. K of H to C by, we use the trace inner product kind of thing. But here it's not Hilbert, I mean, we can make sense here, but this is not Hilbert's with inner product. So phi T of any S equal to trace of ST. We can write ST, TS, doesn't matter. We have shown that trace of ST is same as trace of TS. So for all S in K of H. For all compact operator, we define a linear functional like this. Then this is one thing. And similarly, we want to have the same definition, but on different spaces. So for T in B of H, define. So we use the different notation because it's a different linear function on a different space from B1H to C by, I mean, all these things make sense because trace class operator is an ideal. So chi t of any s equal to trace of, again, st for all s in B1H. This is very similar to, I mean, in the L1 space, we will sum it, and here we are taking the trace, which is the non-commutative sum. That's all. So we define it like this. Then the following theorem is true. The theorem is T going to phi T is a Banach space isomorphism, meaning it's an isometric isomorphism. Maybe I will write isometric isomorphism. Is an isometric metric. Is it clear what I have written? Isometric isomorphism between, so initially we used phi t, so between k of h star t going to this, no? So we have to use the other way. Between B1H to k of h star. Okay. So that whatever we have written as t phi t going to phi t is an isometric isomorphism between B1H to kh star, the dual of kh, dual of compact operator. Similarly, t going to chi t is also is an isometric isomorphism. Isomorphism between trace class operators to, sorry, from B of h to the dual of trace class operators. Okay, B1 is star. Okay, so we want to prove this. Okay, I mean, we haven't done any proof. I mean, we haven't even proved that it is bounded or anything. We have just written some notation. It's just a definition. So let us prove everything. Yeah. First, we consider the duality for compact operators. So let T be a compact operator. No, let T be in B1H. Okay. T be B1H. Then phi T of S for S in K of H. Take a compact operator. Then phi T of S, which is equal to trace of ST. Take the mod. Okay. Now we have proved this inequality, which is less than or equal to norm T times trace of mod T. We have proved this crucial inequality. And this implies phi T is bounded and norm phi T is less than or equal to norm S. Okay, so we have proved one way. Now we have to prove that, we want to prove that it's an isometric isomorphism. So we have to prove that the norm phi T is exactly equal to norm S. Okay, so that can be, so that we used the trick already several times, at least 2 times. So that is to, I mean, when you want to find, when you want to prove inequalities on trace, you first use, I mean, you use the finite rank operators and then take the, I mean, you prove it for all arbitrary finite rank, hit the operator by a finite rank operator, arbitrary finite operator, and prove the inequality. Then you can remove that because it's a finite sum. Okay, the trace is an infinite sum which can be approximated by finite sum. So let P be a finite rank operator, finite rank projection. Then trace of P mod T. Okay. So now I don't have with mod T, so I use this inequality. So this is the trick we should have used earlier. So I used to use U star T, okay, where T equal to U mod T, polar decomposition. We have used it several times. So we use that is equal to this trace of P U star T. Now we know that that is less than or equal to norm of P U star times trace of mod T. Okay. Now you know that P is a projection which has norm 1 and U star is a partial isometry that also has norm 1. Partial isometry is isometry on some subspace. I mean, it is 0 on one subspace and it's isometry on the orthogonal subspace. So that also has norm 1. So you can take out, I mean, the product will have norm 1. So that at least less than or equal to trace of norm. Okay. Now, what did I write? Sorry. I have written something. I mean, I have gone back. Sorry. This I don't want this. Sorry. I mean, sorry. This is to write. This is equal to this. I'm sorry. I mean, this doesn't give me anything. I want to prove that. See, I have proved that norm of Phi T is less than or equal to norm of S. I want to prove norm S is less than or equal to norm Phi T. Towards that, I have to do the following. So this is basically you multiply by this. This is nothing but P U star, right? That is what I want to use. So, I mean, that is how the phi t is defined. So, phi t u star, sorry, phi t u star, right? Now, this is less than or equal to norm phi t times norm p u square. Okay. Now, you use that as norm 1. So, this is less than or equal to norm phi t. So, this implies that what we have proved is trace of p norm t is less than or equal to norm phi for all p finite rank projection in H. Okay. So, this implies trace of norm t is less than or equal to norm phi t. Okay. This is true for all finite rank projections. So this is true. So this implies norm T1, the trace norm of T is equal to, we have already proved the other inequality is equal to phi t. Okay. So we have proved the equality. Okay. Okay. So okay. So what is next? So now we want to prove it's surjective, right? So we have proved we have a map defined between trace class operators taking values in k of h star. Every operator t in trace class operator, we have defined a linear functional on k of h, and we have shown that preserves norm. All we have to prove that it is surjective. This association is surjective. So to prove surjectivity, of t going to phi t, this map. Suppose phi is in k of h star. Okay. So we want to produce a t. We want to produce a t, a trace class operator such that phi is equal to phi t. Okay. How do you do that? The first thing, notice that B2 is contained, B2H is contained in K of H star, K of H, and you can restrict the feed to B2. Okay, and that's a Hilbert space. And Rees lemma will give you a T. So this is our idea. So we have a linear functional defined on all compact operators. Trace class operator is contained. The trace class operators are compact operator. So you can restrict this linear functional to Hilbert-Smith operators, and that's a Hilbert space. So in Hilbert spaces, linear functionals are given by the elements of the Hilbert space itself by Rees lemma. So you get an element in B2H. Now you prove that is actually not, I mean, that's not just Hilbert Smith, it's actually trace class. I mean, trace class operators are a proper subset of Hilbert Smith operators. So you prove that is actually trace class. So once we do that, then that phi t, this will coincide. Okay, because that is how it is defined. So since B2 here, so but we have to get a linear functional B2H, means we have to prove that this map, whatever phi, is actually bounded with respect to the Hilbert-Smith norm. Okay. Now for S in B2H, okay, phi of s is less than or equal to norm phi times norm s. But we have already proved that norm s is less than or equal to norm s2. We have already proved the any our operator norm is less than the Hilbert-Smith norm. We have proved that. So this implies, consider, I mean, we get the following. On B to H. Okay. Now we can consider phi as a linear functional on B to H. We get a T in B to H such that it should satisfy the trace thing. So such that phi acting on that T, phi acting on any S is equal to the inner product, right? Inner product. What is the inner product? TS, the Hilbert-Smith inner product. But then that is equal to no, it will be a, sorry. I mean, we get a T. You can take it T star if you want. Okay. There exists a T star. It will be the other side. So that is equal to ST. It should come the other side, no? ST star. And that is equal to trace. So that is equal to trace of ST. Okay. Now we have got it for all S in B2H. Okay. This is okay. This is the Hilbert-Smith inner product, and we get this. Okay. Okay. So now we have got a Hilbert-Smith operator T, such that this phi restricted to this Hilbert-Smith operator is given by this. I mean, it has the same value. I mean, it is indeed bounded in the Hilbert-Smith now that we don't need anymore. I mean, only to get this operator, we need this. Okay. Now our claim is the following. First claim is something is not writing well. Now the claim is T is indeed in B1H. Okay. So if we prove that T is in B1H, then it will imply that, and it, I mean, then it actually phi is equal to phi T on Hilbert-Smith operator. And if it is T is in B1H and T, I mean, T coincides, then phi T will be equal to phi, right? Is that clear? If T is in B1H, if we prove T is in B1H, then that will imply that phi T and this phi coincides on finite rank operators. It coincides on Hilbert-Smith operator. It should coincide on finite operators. And phi T is in B1H means phi T is bounded. Okay, so it's also a bounded operator. And two bounded operators coinciding on a dense subspace are equal. Okay, they are same. So we only have to prove this. If the claim is proved, let me write. Then phi is equal to phi T, since they coincide on dense subspace, right? They coincide on all Hilbert-Smith operator, which contains finite rank operators, and finite rank operators themselves are dense in compact operators. So this is enough. Okay. So if the claim is proved, then so we all we have to prove T is in B1H. Okay, so why is T in B1H? No, again the same trick, I think. Trace of, so for P in, yeah, because it satisfies the same trick. There is really nothing new. I'm sorry. So I have to do the same thing again. So this is P, suppose P is a finite rank projection. I use the same thing. Okay. Then trace of P mod T. Okay. I mean, P mod T makes sense. Okay, it's positive operator. I have to prove it's finite, but as a positive, I mean, you can take a P here and you can write P instead of P, P square, and you can bring this P here if you want. Okay, so this makes sense, which is equal to trace of P U star T. Okay, if you just write the infinite sum, and that is equal to phi of P U star trace less than or equal to trace of mod T. No, so again, I'm doing the same thing. So that is less than or equal to phi of Pu star times that is equal to norm Pu star times norm. Okay, because it's a because that is because I mean, since mod T is in mod T is a Hilbert-Smith operator, so this is true. Okay, this is Hilbert-Smith operator, so this is true. I mean, we have mod since mod T is in. I mean, you have to go from here. Since mod T is a Hilbert-Smith operator, trace of P mod T is by definition is equal to this. But then we have defined that phi of s is like this. I mean, this formula holds on Hilbert-Smith operators. So because of that, so this is maybe I will write one more step. So this is equal to phi of Pu star. Okay, that is equal to less than or equal to norm of Pu star times norm phi. So this implies trace of P mod T is less than or equal to this is equal to norm phi, of course. Less than or equal to norm phi. Okay, for all P in f of h. So this implies trace of norm T is less than or equal to norm phi. So this implies T is in B1. Okay, that is the claim. That is our claim. Okay. Please ask me if this is not okay. What we have done is the following. We are proving that the T going to phi T is an isomorphism between the dual of compact operators and trace class operators. So given a trace class operators, we can define the linear functional using this prescription. And so that is a bounded functional. And we want to prove the subjectivity. So given a phi, we can restrict that phi to Hilbert-Smith operators. And because it is a Hilbert space, there exists an element in the Hilbert-Smith operator, which is an operator, Hilbert-Smith operator. And that gives that evaluates the phi using this formula, using this trace formula. So then we prove that T is actually a trace class operator by this. And for that, we use the same trick. To prove trace class operator, we have to prove trace of mod T is finite. Okay, so we take trace of mod P mod T for some projection. And that is a Hilbert-Smith operator. P mod T is a Hilbert, in fact, it's a finite rank operator. So that you can write it like this, phi of this, then using the boundedness of phi, we get that it's all direct. Okay. Using the boundedness, we get this. Okay. So any question? Okay. So if there is no question, I will go to the next step. So this proves that the first one. Okay. This proves the first statement that T to phi T is an isometric isomorphism. Right. So now to prove. Now suppose. So next step we want to prove is suppose T is in, we want to have T is in B of H. We want to prove, now to prove, so maybe I will write it. So trace class operators, B of H star is isomorphic to B of H. Okay. Now to prove this, so we have already given this association. This is T going to chi T. Okay. So if T is in B of H, then chi T of S is equal to trace of ST for all S in B1H. Okay. Then this norm of mod of chi TS is equal to mod of trace ST is less than or equal to norm S times trace norm of no, we want to, so S is in B1, norm S1 times norm of T. Okay, so this implies norm, the operator norm, the linear functional is less than or equal to norm S1. So we have to prove the norm is equal. Oh my God. Oh shit. Okay, the meeting will end in 10 minutes. So I did not inform Krishna and it may be too late now. So you log in after 10 minutes. Okay, when it ends, you all log in after 10 minutes. I'm sorry about it. So because since we have changed the class, I forgot to inform you. Okay, I'm sorry. Okay. Sorry. So okay, what are we trying to prove? We have proved this. We have to prove the other way. We have to prove that norm chi T is less than or equal to norm S. Actually, see, if you see in the earlier proof, we first proved that norm phi T norm phi T is actually equal to norm S. We proved the other way inequality, but we use the same thing later. So here, let me prove in the end. Okay. So this also we will prove in the end. So for the time being, let us assume that this norm chi T, this is only norm chi T is less than or equal to norm S1. The other way inequality, this way we'll prove in the end. Okay. In the end of the proof of this proposition, it will automatically follow. That's what happened. I used the same idea twice. So I will do this in the end.
I'm in a class. I'll call you back.
Say it again. What did you say?
So should it be norm T instead of norm chi T is less than or equal to norm T?
You are right. Yeah. Norm T is less than or equal to norm T. Correct.
Thank you.
Yeah, there is no yes here. You are right. T is the operator. S is the variable, of course. Okay. So we'll prove in the end. So okay. So now we have so this implies that this anyway implies that chi T is a bounded linear function. Chi T is in B1H star. Okay, so we have anyway, this is true. We have to prove the isometric property for that will follow in the end. That's what I'm saying. Okay, so we have phi T is B1H star. Okay, now suppose chi is some arbitrary linear functionals on B1H star. Okay, so we want to get a T. So how do you get a T? So here, earlier we used the Hilbert-Smith idea, which we cannot use here because this is defined on trace class operator, which is a smaller subspace than Hilbert-Smith operators. So we have to do something more. But here also we have something. We have these finite rank operators. There are some particular kind of finite rank operators called rank one operator. So I have to define it in the middle of the proof of something. I'm sorry, but this is the definition. For xy in Hilbert space, okay, you can define operator T comma xy. Usually this will be defined as tensor, but that might be confusing. Usually you will write it as x tensor y. The x tensor y is an operator, but that can be considered as an element in the tensor product also. Actually, both are same. Okay, but in some sense, in some identification, but not to confuse with that, I write it as txy. Okay, txy is an operator from H to H, a rank one operator, which is defined as txy acting on any z is equal to you take the inner product. So Z should come here because it's linear, and ZY times X. Okay, this is just a one rank one operator. I mean, the range is, this is the range of TXY equal to CX, right? So this is for XY in this. So this is defined for all Z in H. Okay. So you define TXY acting on Z is just take the inner product on Y and then multiply this X with that complex number. The inner product is a complex number. So multiply with that. So this will give a rank one operator. So this is range. Range of TXY is just one-dimensional vector space spanned by this is X. So this is what is called a rank one operator. Okay. So once we have this rank one operator, so this is clearly bounded because the range is just finite dimension. So this is bounded. So, okay. What is it star? TXY star. To compute TXY star, let us do this to compute. Let us, because we have to use this TXY star. So this I will leave something as an exercise. So you can leave it as an exercise, but I will do something. One verification I will do. Okay, to find TXY star, what will you do? You take an Z and you take TXY, right? No, maybe TXY star here. Let us just see what we will get. Okay, what we will get in the other end. That's what TXY. Okay, TX. So the operator will get on the other side. That's what TXY star is. Okay, Z prime. Okay, so what we want to get an operator on the other side, the inequality. I mean the equality, and that is what actually TXY star is. Okay? So this is equal to, let us compute it. So this is going to be ZYX, right? ZYX, Z prime. So now this is equal to ZY X. You can take the inner product out. X Z prime. Okay. Now you can take this. So I want to take it to the Z prime side. What do you want? I have Z. Yeah, X Z prime. So I want to get TYX. So X Z prime. I have it there, and then so I can take this Z. So this will become Z prime because it's a conjugate. I mean, say the second variable in the inner product is conjugate linear. So I have to take the Z prime X times Y. I can write it like this, right? Now this is equal to Z comma T of YX of Z prime. Okay. So I haven't done anything. I've just used the definition. So this is true for Z prime in H. Okay. So this implies TXY star is equal to TYX. That's all. Okay, that's all. Okay. I mean, there is something nice about, see, okay, I will tell you after after proving this, I will tell you. See, this is the problem with the assumption of mathematicians, the conjugate linearity, the linearity in the first variable, conjugate linearity in the second variable of this inner product. We are using in mathematics. There's a problem with that. Physicists use a different notation, and that is very useful. So I will come to that later. So here I defined the rank one operator TXY, and I proved that TXY star is TYZ. Okay. So why do I do that? So let this be here. Now I want to do the following. So what I have is the following. So now we want to prove the following. We have a linear functional defined on all trace class operators, and this is a rank one operator. In particular, it's a finite rank operator, and it's a trace class operator, and we have to find its trace, and we will do it in the proof of the proposition. Now we want to define a bilinear form. You know that you can define a bilinear form, not bilinear form, this sesquilinear form. I mean, I think Shruti used all that. I mean, so let me define it. To define adjoint, you use something like bilinear form or something. Not bilinear form, a sesquilinear form. Define B xy. Okay, for xy in H, bxy equal to use that chi of txy. Txy is a rank 1 operator, and you have this chi defined on trace class operators, so which you can define on that, and you define this linear function. So B is linear in first variable x and antilinear, conjugate linear in y variable. Okay, and we have to prove it's a bounded sesquilinear functional. Then bounded sesquilinear functionals corresponds to linear operators. That is, if I mean this, I think it's used to define adjoint. So if bxy is a so this is what is called sesquilinear form.